So you're probably most used to writing C code. C code is what you're often using for your design level. And you might have written some assembly code as part of some of the other courses, right? So, but what you may not have done is actually looked at the C code and how that's converted to assembly and what that actually looks like. So this is really useful in reverse engineering, because in reverse engineering, the best we're going to get is assembly, and recognizing some common structures is incredibly helpful in understanding, what C code is doing. So we're going to use something called Compiler Explorer. If you go to godbolt.org, so someone, Matt Godbolt, started this project. It's open source now with quite a few people contributing. But basically what you have is on the left side of the screen, we can put in C code. And on the right side of the screen, we're going to get assembly. If we go to use this, so I'll pull it up here in a second. Basically, the only important thing is make sure you change the compiler type. So by default, it's going to set it to x86-64. So this would be like compiling for your computer. We want to change it to ARM GCC. And I'm going to in particular point you to use this one, ARM GCC 9.2.1. So we're just looking at some sort of more generic ARM code right now. And we can select different versions and see how that translates. It'll give you some default example code when you do this, right? So it should look something like this. So we have C code on the left. This is doing a simple square operation. And we have the resulting assembly output on the right. Okay, so what can you do with that? The thing we can do with that is understand what the compiler is doing. There's a few caveats, right? So a big caveat here is that it applies optimization. And so if your code does nothing, it might get optimized away. So if you look at the assembly and you say, hey, where is this code? This doesn't make sense. Check if it got optimized away. There's some color coding between left and right. So it'll try to point out where stuff came from, which can be really handy. You can also call external functions. So if you call something that isn't defined or isn't part of your file, like printf or something, normally it will put the function call in there, but it won't show you the disassembly of it. So we're going to try the following. We're going to try a for loop, and you should open up godbolt.org and follow along to see how this works. We're going to try some addition operators, multiply operators, and we're going to try calling other functions. So yeah, let's pull up the Godbolt. Okay, there we go. So this is what Compiler Explorer looks like. So you can see on the left we have the C code. On the right we have the assembly. So it will remember if you've selected your drop down already. So you just go here, and it's actually right at the top in this case, ARM GCC 9.2.1. So there's just a function. You don't need like a main or anything like that, right? And so if you change something in here, it just automatically changes the assembly. So for by default, it had some square in here. So we can make a loop, for example. So if I call it imp loop, and you could make it return nothing. So void loop void. And so when I generate just a loop, and this is something we'll talk about in the next lecture really quickly, you can see it generates some stuff. So this is part of the function setup and return features here. So we see that. But yeah, let's just make an int I, right, for I equals 0. Let's see what happens. And so you can see, so in this case, I was afraid it would optimize it away, but it did not. What you can see here is, you have the variable, we have a loop here. So you can see as I highlight this loop, it sort of highlights on the right side here. And this is what I was talking about. There's some sort of like color matching. Okay, there you go. So I've done something like when I selected it. It's doing a funky thing, but you can see these two are associated. And basically what the goal is going to be in the first quiz is you're going to actually be asked what a few certain instructions are. So you'll have to dig in a little bit about how the assembly works, but you can basically say, if you've looked at a little bit of assembly before, this is loading something here into R3, comparing R3 with some constant number, and this is the constant 9, right? And depending on that value, it's either breaking to this label here, L4, or it's going to continue this loop. So this is actually how we're doing the iteration loop here. We can explore other stuff, so let's just call this test, not even loop, doesn't really matter. All right, because this is maybe even a little more complicated, so we can make even easier functions, because if we want to try like an addition, right, I equals I plus 5, and the question is, does it optimize it away? It didn't in this time. So you can see it's loading some value R3. You'll notice I didn't initialize this, right? So this would be bad C code, and if I add an I equals 0, you should actually see, right, R3 is now set to 0. So as you change the C code, you'll see the assembly change. So if we comment that out again, comment that out. Oh, right. I need to comment out the I equals 0 part. Yeah, so you can see it just creates R3. Doesn't actually initialize it to anything. Or not create, sorry, starts using R3. So here we set R3 to 0. It's storing it away to some memory location and then loading back from memory, adding, and storing it back. So we can see that happen. And we could try different functions, right? So you can see what happens when you're doing all this different stuff. Interestingly, so when I ran this multiply, right, you can see here it's actually done some optimization, because you can see it's doing a left shift and an add. So if I change what the multiply is, change this to 2005. Oh wait, no, because this is 0. So it is doing some optimization here. So you may have to change stuff to actually get some of the more intended behavior. Let's see if we can force it to use. What I'm trying to see is if there's some multiply operation that's going to come up instead. So let's make this a function. So now it knows nothing about A and B. Okay, so there we can see, so what's interesting is that it was avoiding using this multiply for some time, so we could see when it knew something about it, it was actually doing some optimal version of it. So if it's multiplying by 255, this is actually equivalent almost to a left shift, right, by 8. So this is like bit math type things, right? So if you shift left by 8, you become almost equivalent. Then I think it's going to just subtract it. Yeah, so it subtracts 1 off at the end or something, or subtracts 1 value of it. If we go by 255, it's exactly equivalent to a left shift by 8. If we go to 1024, it's exactly equivalent to a left shift by 10. So you can see various optimizations the compiler is doing. All right, so as you explore, just make sure you're not viewing only an optimized version of it. The other thing that you should check out is if you call other functions. So if I make, let's just call A times B, right? So if I go void, test void, right, mul 7 9. Did I mess something up? Maybe it wants this after. So we'll see if something happened to me. Okay. Anyway, so you can take a look how that works on your own to see how the compiling goes. So I'll wait for the site to come back in a second here. Luckily, that's one of the things I have up on the slides here is what it looks like when you call other functions. So calling other functions is often a pretty, obviously it's going to happen quite a bit. What you'll see is basically one of the important things is how the variables get passed. So, oops, there you go. We'll see a branch to another function here. So you can see this BL is calling this other function. And this function up here, right, is then doing something. In this case, all it's doing is adding the two numbers together. But the question is, how did it get those values to that function? And so you can see we passed 4 and 2 to the function, right? And so you can actually see some of these constants here. So by playing around with the constants, you can figure out which registers are used for passing which functions. Or sorry, which registers are used for passing which arguments, right? So if we go back, let's start working again, to my example I had with the multiply up, right? If we look at the call to the mul, you can see the 7 and 9 here. And what if we make this take another variable c, right? Now we need 12. I'm just putting random numbers in here. Right, so we can see now it's using a different register to pass that value. So you can explore that a bit to understand how the calling convention works. And the big questions, the one I'll sort of experiment a bit with is, I'll have you experiment with a bit, sorry, is when you're calling the C function, extend how many arguments go in and then see what happens. So you can do this with a really long function if you want, so it looks a bit silly, but it'll help you understand. So if you add one argument at a time, at some point it stops passing them in registers, and at some point it starts passing them on the stack. So you'll see some change in how the arguments are stored. So all you would do is, if we go back here, right, is I'd continue to add this, and after this you can then figure out what happens at some point. What should happen is it will also, if you pass different types of variables, so if you pass an array, it's going to look differently. So 56 here. So what you can see is that, right, it went R0, 1, 2, 3, and then all of a sudden what's going on here, right? It's not using R4 like you maybe just expected. It's instead putting 56 into R3 first, storing R3 onto the stack, and then using the rest of the registers again, right? So at some point it starts using the stack, which is what we expect from typical sort of function call setup. But yeah, so if you can explore with that a bit, you should be able to figure out what it's trying to use for different types of variables. So if we change this to chair, I don't think this will change anything, but we could just see. Yeah, so that changes nothing. But if I change this, so if we go back to 3, change this to, and we'll just force this to be a pointer. You can see if that affects anything. No, so it's still passing the function pointer, or not the function pointer, so the array pointer on the stack as well. But yeah, so that's sort of one of the cool things you can do with Compiler Explorer is you can really figure out how different stuff actually works on this thing. So you can sort of understand a lot more deeply how the compiler is working. And what it looks like when it does different things compared to, if you change, like here we did loops versus multiply versus adds, but you can change all sorts of stuff and see how it affects the results.